Okay, this time we'll be looking at cyclohexane chair conformations. So the first thing I want you to do is I want you to watch this video. So it starts in the chair. You get a half chair, a twist boat, a twist boat, a half chair, and a chair. I'm going to let you watch this one or two more times because this is a helpful demonstration, and we'll elaborate on it more. You just need to get a little bit comfortable with it right now. Alright, let's talk about what we're seeing. So, first thing is, why is cyclohexane doing this? Or why does cyclohexane have what we were calling a chair conformation? Well, what you'd expect from your drawings is that you've seen this probably several times by now. Cyclohexane looks like a hexagon, or that's at least how we draw it. The problem with this is that if you draw it as a hexagon and it actually in three-dimensional space adopted the configuration or the conformation rather of a hexagon, what you'd see is that each of these angles would be 60 degrees, right? So if you have 360 degrees, you'd have 60 degrees here. Well, if you remember, typically when you're looking at cyclohexane, you're looking at an sp3 hybridized carbon at this point. So the bond angle would prefer to be 109.5 degrees. So when you have the chair conformation, and this is how we draw the chair conformation, hopefully you'll see why in a little bit. This is why cyclohexane does it. It reduces the strain energy due to angle strain from going at 60 degrees, which is totally unfavorable, to 109.5, which it wants to be because it's sp3 hybridized and it wants to be tetrahedral. So let's talk a little bit about what we saw in the video. So this again is our chair, and hopefully you see why we draw it like this. You'll actually see this shape located in here with these black carbon atoms right here. Okay, so that's why we draw it this way. So when you have this chair, you'll notice two different groups. Hydrogens that have been drawn red and hydrogens that have been drawn blue. So these red hydrogens, which we'll draw on our chair like this, are what we refer to as equatorial. If they're equatorial, they have a few properties. First is that if you look in 3D space, these are located what you could call horizontally in the plane of the ring and located pushing away outwards from the ring. This makes them relatively stable because if they're pointing away from the ring, they can't be having many what we'll call steric interactions with the ring. A steric interaction just means that the molecules, well, these substituents over here are getting too close to the ring, and you have their electron clouds hitting each other, and that's repulsive, and that's not so favorable as far as energy goes. So when we say a steric interaction, that just means things being too close in space. Also, when we draw the equatorial substituents, notice the geometry that we see in our 2D chair. This is parallel with this, and that's parallel with these two equatorial substituents. Similarly, this red line over here and this red line is parallel with these two inner bonds within the chair. And lastly, these two over here are parallel with the edges of the chair located here. Okay, so what's going on with the blue hydrogens then? Well, again, if you look at our chair, you'll see that these are substituents that go up or down vertically in space. So literally along the z-axis. If you're going to imagine this plane here of the chair, if you're going above the plane or below the plane, that's going in the axial direction. So axial substituents are considered less stable than equatorial substituents. The reason for this is that they're closer to the ring and they have a higher chance of whatever is located here being too close to other things, either the ring or other axial substituents. So there's one other very important characteristic when we're talking about chair conformations, and for that I want to go back to the video. So let's rewind it to the point where we're at the beginning. I want you to focus on this substituent back here, this blue hydrogen located up here. Notice that first it starts directly upward in the axial position. Notice now that we are in the other chair conformation. Remember, it was in this location, now it's in this location. Or what you could say is it went from axial to equatorial. Let's slow down and take a closer look at that. So it started here in the back over there, and when everything was said and done, after going through the entire procedure, going through the half chair, the twist boat, the boat, back through another twist boat, another half chair, it finally got here. Actually, I think I even labeled this one wrong, because we said it was over here. So notice this started axial and now it's equatorial. Notice that in fact all of the blue axial groups, once the chair has flipped, are now equatorial, and all the red equatorial groups are now axial. So that's another property of chair conformations, is that in general there are two chair conformations, and as the molecule vibrates and moves around in space, it's constantly flipping between these two chair conformations. It goes through that half chair, twist boat, boat, twist boat, half chair, all the way back. And it turns out that the chairs are the lowest points of energy. Everything in between is higher in energy. So again, the concept to remember here is you have a cyclohexane chair conformation and you have a substituent that's axial. If you go and you do what's called a ring flip to the other chair conformation, and there's only two chair conformations for any cyclohexane ring, then the axial substituents will become equatorial, and likewise the equatorial substituents will become axial. Okay, that's about all the information you need theory-wise. Now we do the slightly more difficult, well, you'll see. So here's our dilemma. We have a skeleton. How do we get to the chair? And this is what you'll see is the trickiest part of working with chair conformations. And this is the trick. If you want more information on this trick, I suggest you pick up Organic Chemistry as a Second Language by David R. Klein. So we consider, when we have the cyclohexane skeleton, is that whenever you see a wedge, that will be considered up, and a dash, that will be considered down. Now those are very important that we get those correct, and I'll try to elaborate as much as possible as we start solving problems. So this is your basic outline of a chair. Now, I've already numbered this, but this one corresponds to this carbon over here, and so on and so forth. So if we see a wedge, we want that substituent to be up. Now, what do I mean by up? Let me define it even more strongly. Up means above the plane, down means below the plane. Plane is the ring. So if you're above the ring, you're up. If you're below the ring, you're down. So, very important point to make here. At the one position, this is axial and this is equatorial. We would call this up because If this is the plane of the ring, it is located above, and we call this equatorial substituent down. Similarly, if we go over to the 4 position, axial would look like this, and equatorial would look like this. We would call this down, and we'd call this up. So what I'm trying to say is equatorial can be up or down. Axial can be up or down. Don't confuse axial with always being up or equatorial with always being down, and a lot of people do that. And let's reinforce that by looking back here. If you're looking at the axial substituents, the first thing I'll tell you is that I always choose this to be the first one in the ring, and then I go around 2, 3, 4, so on and so forth. What you should always remember when you're making your axial substituents is that you're going up, down, up, down, up, down. I'll say that again. Starting at the 1, you go up in space. At 2, you go down in space. At 3, you go up in space. 4, down. 5, up. 6, down. You'll see that the corresponding equatorial component must be the opposite of whatever the axial is. If you look up here, where this is 1, you'll see that if the axial is up at 1, the equatorial must be down at 1. If we're looking at 2, if the axial is down, the equatorial must be going up. Okay? So let's try to figure that out and make our leap from the skeleton structure to the chair. I'm going to tell you it will look like this. Okay, so again, how do we get here? At the 1 position, that is a wedge. That means up. You have the choice. It could either go axial or equatorial. In this case, axial will be up. So the methyl group goes up in space like this, axial. Over here, we have a dash. That means Cl is going downward in space. If we're at 2, remember at 2, if the axial at 1 was going up, the axial at 2 will go down. If we're at 3, we're at a dash. That's again down. That'll be equatorial, because remember the axial will look like this. That'll be up. If we're at 4, we're at a wedge. That's up. The axial goes down, so you choose the equatorial. If we're at 5, the chlorine is again going down. Notice the axial goes up. And at 6, you're again on a dash, so you want the chlorine to go down, which is again axial. Hopefully you have a partial understanding of what's going on right now, but I'll tell you that the simplest way to learn how to do it is to simply do problems, get it wrong, and then learn it that way. So I'm going to give you some problems. Well, actually, there's one more important thing that I want to discuss. So this is the first chair conformation. What would the chair flip look like? So again, remember, every cyclohexane has 2 different chair conformations, and it flips between them. So if this is one chair conformation, remember the rule. Everything axial becomes equatorial, everything equatorial becomes axial. So over here, if we wanted to flip this, we would take all of the components and they would flip. So notice here, the methyl at 1 was axial and now it's equatorial, and the chlorine that was axial is now equatorial. Now, maybe this point will be lost in you at this point, but hopefully it'll make sense eventually. If you convert this back to the cyclohexane skeleton, what it will look like is actually this. So remember, we don't care necessarily about the dashes or wedges, we care about the relationships. If both of these are dashes, that says something, that says they're cis. And if all these are wedges, that also says they're cis with each other. If something is a wedge and then a dash, that means they're trans. So there's 2 ways to represent the cis-trans geometry. You could do it with this, or you could do it with this. This is actually the same molecule looking at from a different view. You've actually just flipped it upside down. And if you're looking at it in 3D space, that'll correspond to the cyclohexane chair flip. So it'll be going from this to this. Alright, let's try some problems. So the first problem is, it's It's asking for the more stable chair conformer of trans 1-ethyl 2-methyl cyclohexane. So I'll show you how to do this one. The general procedure for solving this problem is always going to be draw the cyclohexane skeleton, number it, draw the chair, number the chair, draw the substituents, flip the chair, compare the chairs. It'll make sense as we start doing problems. So here you got to remember your nomenclature. It's going to look like this. So 1-ethyl 2-methyl, and it's a cyclohexane. And I've already numbered the chain. Okay, and remember you could do a dash here and a wedge here. It doesn't matter. Both of those will give you trans. You'll just start with a different chair. When you're drawing your chair, remember at the 1 position we're saying wedge is up, so that'll be axial, and at the 2 we want down, so again that'll be axial, because remember when you're filling your axial substituents it's up, down, up, down, up, down. To do the chair flip, all you need to do is take these 2 axial components and make them equatorial in space. Okay, at this point we've already got to 6. Now we simply need to compare the chairs. So energetically, this chair conformation has 2 axial substituents, and this one over here has 2 equatorial substituents. So there's really no comparison here. You know the one with the equatorial substituents is going to be the more stable chair conformation. And you try this one on your own. And it's okay if you get it wrong. These are a little tricky when you're starting off. So pause the video and try it. Okay, I'm going to assume that you tried it. If there's cis this time, and then you either have 2 wedges or 2 dashes. Remember, again, it doesn't matter if you have 2 wedges or 2 dashes, you'll get the same answer at the end. So the first chair you draw will be this one. At 1, axial's up. At 2, remember, because axial is down, equatorial will be upward facing. You then do the chair flip, and what you'll get is this chair conformation. Here we have a little bit of comparison to do. So on this side, the methyl is equatorial and the ethyl is axial. And over here, the ethyl is equatorial and the methyl is axial. Okay, so side note, bulky substituents are bad on axial. And by bulky we mean anything that has more branched carbons is really bad. This is in order of bulkiness. More branched carbons is bad. Then anything with carbons, anything alkyl is bad. And then the smallest, the least bulky, are halides. And you'll see us use these rules as we go through. So again, this is order of bulkiness. If you have a bulky substituent axial, that is unstable. So if you have an ethyl axial, that's worse than having a methyl axial. So the conformation, where the ethyl is equatorial, will be more stable. Okay, try out this problem, and you'll see that they're all the same after a while. As long as you're able to convert between the skeleton and the chair and then draw the chair flip, you'll be fine. Alright, so I'm going to pause again and try this one. Okay, so first thing you need to do is take that nomenclature, convert it into a cyclohexane skeleton. After that, you know once again that a wedge is up, so at the 1 position that's axial, and at the 3 position downward in space is equatorial, because the axial component will come upward like this. When you do the chair flip, it will look like this. Once again, when you're doing the stability, you have an iodine axial versus a methyl axial. The methyl axial is less stable, because remember, methyl groups are bulkier than halides. So this will be the most stable, the other one will be the least stable. try this one now. Pause the video once again. Okay, so once again, nomenclature, convert it to the cyclohexane skeleton. 1 is going to be axial because that's upward. Similarly, 3 is going to be axial. You figured out that a dashed 3 was equatorial, so a wedged 3 is going to be axial. Likewise, once you flip the ring, these will go to equatorial, and when you're comparing them energetically, you have 2 axial versus 2 equatorial. The conformation with 2 equatorial will be favorable much more energetically. Okay, let's just do a few more examples to make sure that I'm hitting this home. So again, pause the video. Once again, there's your T-butyl and your isobutyl groups. And it looks pretty bad. T-butyl is bulkiest. Isobutyl is pretty bulky, but it's not as bad. So having the T-butyl group equatorial is a lot better. You'll actually hear, I believe sometimes people say that the T-butyl group is so unfavorable in the axial direction that I'll actually lock the ring in this conformation and your cyclohexane won't be able to flip. Okay, try this one. Pause. Again, trans 1,4 looks like this. Wedge is up. On 1 that'll be axial. On 4 because up, down, a dashed or a down on 4 will be axial. This will be less stable because again you have 2 axial versus 2 equatorial. Alright, now let's do something a little bit more interesting. So in this problem, we were told that there's 4 cis-trans isomers of this structure. And what they want us to do is give the most stable isomer. So in this problem, you need to realize that you're essentially going backwards. The most stable isomer will have a chair conformation that has all the groups equatorial. So if I were going to number it, this is 1, this is 2, and this is 4. And remember, this numbering does not reflect nomenclature. We're simply numbering the carbons so we can keep track of them. So if this is 1, this is 2, and a 4, I want all of these substituents to be equatorial if I want the most stable chair, the isomer that has the most stable chair conformation. At this point, I need to convert them back. So I'll notice that at 1, we're going downward. At 2, we're going upward. And at 4, we're going upward in space. When we convert that back to our skeleton, that means that 1 will be a dash, 2 will be a wedge, and 4 will be a wedge. Alright, the last kind of problem you'll see is perhaps what I'll call the trickiest. So, from the lecture notes, you should commit to memory that an axial methyl group has 2 Gauss-butane interactions for a total of 8 kilojoules per mole of strain. And you can see this by doing a Newman projection on a chair. And I believe they even have this in the notes. If not, just remember that an axial methyl group will have 2 Gauss-butane interactions. An axial anything will have 2 Gauss interactions with the ring. Okay, and the problem given is this. An SH group has axial to equatorial strain of 5 kilojoules per mole. We want to calculate the energy between conformations of this molecule. So at first, you're going to attempt the problem exactly the same way you attempted the other ones. You're going to number your skeleton, and then you are going to convert that to a chair. I'll assume you know how to do this by now, since you've done enough examples, hopefully. And then you want to ring flip it to the other chair conformation, because we want to calculate the energy between these. So any component that is equatorial doesn't contribute any strain energy. So this equatorial methyl over here doesn't contribute strain energy, and this equatorial SH group also doesn't contribute strain energy. We're told that the SH group in the axial position contributes 5 kilojoules per mole of strain energy. And you'll remember from lecture notes that an axial methyl group has 2 gauche-butane interactions, and each gauche-butane interaction is 4 kilojoules per mole, so that's a total of 8 kilojoules per mole of strain energy. So if we're going from this conformation to this conformation, we calculate the absolute value, or the difference between their energies, and you'll find that that's 3 kilojoules per mole. Okay, there's a slightly trickier variation on this problem. We'll take a look at it. So here we're prompted once again to give the two chair conformations of this molecule. Since by now you should know how to do this, I'll just put them up here. Okay, at this point they want us to then, if the energy difference between this chair and this chair is 6 kilojoules per mole, what is the energy between the gauche and anti-conformations of CH3, CH2, CH2, Cl? Okay, so this is worded kind of strangely, but I'll try to translate exactly what they're trying to say. Really, they want to know the axial to equatorial energy of a chlorine with one gauche interaction. Because remember, axial components give 2 gauche interactions with the ring. The methyl gives 2 gauche interactions with the ring for 4 times 2 equals 8 kilojoules per mole of strain. So again, pretty similar problem, but this time we know the energy difference. So again, equatorial components, this methyl group and this chlorine over here, don't contribute any strain, but we know that the methyl, when it's axial, contributes 8 kilojoules per mole, but we don't know what the chlorine contributes when it's axial. We know the energy difference between these chair conformations, but we don't know the energy of the chlorine. That's one of the things we're solving for. So you can model this in 2 ways. You could say that the left conformer minus the right conformer will give you an equation like this. Remember, the energy difference is 6, and if you solve that, you'll get x equals 14. Now if you do the right minus the left, you'll get something different. You'll get 8 minus x equals 6, and x equals 2. Only one of these can be right, and this goes back to those rules that we were talking about before, with high energy axial will go to bulkier groups. And remember, our order was branched alkane, straight alkane, halide. So we know that the methyl group should be higher in strain energy than the chlorine. So if the methyl is at 8, we know that the chlorine must be at 2, because how could the chlorine contribute more strain energy than the methyl if we'd taken this to be true? How could it contribute 14 as opposed to 2? So this is the equation we'll accept as true. But remember, we want the difference in energy between the gauche and anti-conformations. This is the final tricky part of the problem. There are, since we solved for x, 2 kilojoules per mole in 2 gauche interactions, because remember, any axial component will give 2 gauche butane interactions with the ring. So if we're talking about 1 gauche interaction, we need to divide our final answer by 2. So we'll get 1 kilojoule per mole of energy in 1 gauche interaction between this and the ring. Okay, so chair conformations, not so bad if you get practice, and if you understand what's going on here, how they look. how to flip between them, and how to convert between the skeleton and the chair. Again, if you're having problems with this, I suggest you pick up organic chemistry as a second language. There's an entire chapter in there that deals with the translation from this to this.